open set. So we define, in our last class we have considered neighborhood and limit point of a set. Now we consider open set. So we define open set as follows. A subset A of a real number R is said to be an open set. That is, this set A is said to be an open set if A is the neighborhood of each of its points. So that is, if A is the neighborhood of each of its points, then it's said to be an open set. And this definition will let us to get another definition of open set as follows. We say that a set A is open if for every element inside it there exists a neighborhood n of x. That is, there exists an open interval that is containing x, such that s in the open interval must be a subset of A. Then we say that A is an open set. So this is the definition of open set. Remember, our n is an open interval. That open interval, this n is a neighborhood, which simply means an open interval. But which open interval? The open interval that contains s. That is how we said neighborhood of x. That is, open interval that contains s. That is the meaning of neighborhood of x. So that is what we are trying to say here. So, and we have said in our last class that this will be this. This is A comma B. So that is it. So for all epsilon is greater than 0. So we have done this before. So let's quickly get a theorem from this place. Every open interval is an open set. So that's the first theorem there. So what happened? Let's consider an open interval. Consider an open interval A comma B. So let's consider an open interval A comma B like this. Let's say we consider an open interval A comma B. So let's consider another interval inside, which is C and D, and this is X. So from that place, I will write it like this. Let C and D be any real number such that C is less than or equal to less than S, less than D. That is what we are trying to write here. So that is, you are considering a neighborhood, another neighborhood of S inside this open interval A comma B. By what we have here, so we see that A is less than C, is less than S, and then we also see that S is less than D, is less than B. So if you match all this together, this will be A is less than C. By transitive law, is less than S is less than D, is less than B. So from this place, we can write it as A is less than S, is less than B. So this simply shows that S belongs to A is A comma B. Now here simply shows that S belongs to C comma D. So, but we know that C comma D is a subset of A comma B by what you have seen here. So since it's a subset, we can now write it as belongs to C comma D, and C comma D is a subset of A and B. So that simply means that A comma B is an open set. Remember, A comma B here means an open interval, and the theorem says every open interval is an open set. So for us to show that it's an open set, we need to create another neighborhood, because by definition the theorem says there exists a neighborhood of X. So we need to create a neighborhood of X. This is the neighborhood of X. So when we now create the neighborhood, we must have that the neighborhood is a subset of S. And how do we do that? If you have shown that if you have picked an element in it, which is S, if it is inside this C and D, the element must also be inside A and B. And A and B, C and D must be subset of A and B, which we have seen here. So which you have seen from this place. So in that case, every open interval is an open. That completes the proof. Let's consider another theorem. Second theorem, the union of arbitrary open set is again open. So we need to get the collection of open sets. So let's write it as this. So we start by saying let this I be collection of arbitrary open sets. That is, this AI means A1, A2, A3 to infinity like that. So what do we want to show? We want to show that A union AI, which is equal to A, is an open set. And what does this thing mean? This thing means A1 union A2 union A3 like that. So that's what this thing means. So we want to show that the union of all the open sets is also an open set. So we start by saying let X belongs to this. Let X belongs to this. So if S belongs to the union, definitely S will belongs to some of this AI. What that simply means is that let's say 2 belongs to A union B. So it's not necessary 2 will belong to A and B at the same time. It may be that 2 belongs to A or 2 belongs to B. So we can say that S belongs to AI. Because if S belongs to the union, then S belongs to AI for some I. Because it is not all the A1, A2, A3 that this S will belong to. It may belong to some of them. So that is this one we said for some I. For some I means, I is our 1, 2, 3 index number like that. Now, we have seen that if S belongs to the union, then S belongs to each of them. So for some I. From this place, we now say that since AI is open, so or let me say since an open set, since AI is an open set, then so there will exist some open intervals, comma bi. We know that by definition of open set, there will exist an open interval that is containing this X. So and here we have said that AI is open because of the theorem. It says union of open set is again open. So such that S belongs to AI, comma Bi. So this one will belong to AI. So this is since we got this from the definition of open set. So since you have assumed that AI is open, now if S belongs to all this, S must also belong to the union. So since S belongs to it, it must also belong to the union because this one is a subset of all this. So AI is a subset of this. So we can in fact write it as this because AI is a subset of this. So what this thing simply means is that this union AI is a neighborhood of this. So hence A, what's our A? A is all this thing. We have represented all this thing by A. Hence A is a neighborhood of X. So hence A is open. A is open. That is, A is an open set. Because from an open set, we said that if a set A, is the neighborhood of its point, then is an open set. So we have shown that A is a neighborhood of this. So hence we say that A is open or A is an open set. Our theorem 3, the intersection of finite number of open sets is open. So we start by saying let AI be a finite collection of open sets as usual. So our aim is to show that this is an open set. So the proof is related to the proof we gave under the neighborhood. So we can now say that since AI is open, then there exists some neighborhood of X such that what will happen? We have more than one A here. So we are going to have the following. So such that inside this AI, S will belong to this open interval. This is the neighborhood that we have been talking about since. So that, but I don't want to put it here. We just say there is a neighborhood of x. So this is the neighborhood. This neighborhood must contain the x. So in the first one, we use this. In the second set, up to an. So as usual, let this belong to, let our epsilon be equal to minimum of epsilon 1 up to epsilon n. So we are going to have that s is equal to, s belongs to s minus epsilon, comma, s plus epsilon. It must be a subset of s minus epsilon I plus s plus epsilon I. All these are high. All of them must be subset of AI. AI is our A1, A2 up to AN. So since they are all subset of AI, then they will also be subset of the intersection. So we write it as this. So we write it as this. So it's a subset of AI and it's a subset of this. So I can eliminate this and I will write this one and this. S belongs to this. It's a subset of the intersection. So which is equal to A. So from that place, we see that this thing, A, is a neighborhood of X. So hence A is open, or A is an open set. So we have shown that the finite collection, the intersection of finite number of open sets is again open. So let's consider another theorem. So we have our theorem 4 here. So we say that set A is all about open set. We say that set A is open if and only if it is the union of open intervals in it. Now, since we have if and only if here, we are going to prove it in two ways. So what we do is we assume that A is open. Then we prove that A this union, A is equal to this union. Secondly, we now assume that if A is equal to this union of this interval I, then A is open. Now, we first assume that A is open. Now, since A is open, let me write it down. There exists some open intervals containing x such that s belongs to those intervals. So these intervals contain x and all of them must be subset of A. So that is by definition, since we have assumed that A is open. So from this place now, let's put union to both sides. So let's put union to both sides. Let's put union. So this is A. But since I put union here now, it is no more an element. It has become a set. So in that case, we are going to use subset instead of this. So, and union of all these elements means they are all the set of they will become set A. This SI, I will now write it as I because it is union of all of them. They will become A. So that means A is a subset of union this, and it's a subset of union of A is still A by set theory. So, and whenever we have these two like this thing simply means that A is equal to this index AI, BI. So this AI, BI, we can write it as this. So union of all the intervals. So we have shown that if A is open, then it is equal to the union of all the open intervals in it. Now, secondly or conversely, if A is equal to I, if A is equal to this union, we must show that A is open, and it's very easy in this place. So if A is this union, since I is always an open set, we have shown that every open interval is an open set. Don't forget that this I is open interval. So since this I is always open, it's an open set always. So in that case, the union by the theorem we proved. So since I is an open set and union of open sets, arbitrary open set is always open. So that simply means that this thing is open. Hence, A is an open set, or we say A is open, and that completes the proof of the theorem. So meet me in the next video where we talk about the closed set. The closed set and the closed set will depend on this open set, so we'll talk about it in our next video. Have a nice day.